Okay, we're looking at slope fields in this video. So with slope fields, well, we normally know how to solve differential equations. So if we wanted to solve this differential equation, for example, you would integrate both sides. You would get 2x squared over 2. So it's x squared plus c. Sometimes it's a bit harder to solve differential equations, though, and that's why we can use slope fields to have a guess at what the solutions might look like. So to make a slope field, first of all, you're pretty much never going to be asked to make one, but this is how you would do it, just in case it shows up. You never know. M is dy dx, so like the slope is the derivative, and so dy dx is 2x in this case. If x equals 1, dy dx, I might just use the word slope, m, would be 2. So for example, if I look at this slope field here and I put in 1, I'm expecting the slope at the point where x equals 1 to be 2. So the slope at this point should roughly go up 2 every time I go across 1. Now I'm going to draw in a lot of these dashes, so I'm just going to draw it kind of steep like that. So we're trying to draw slopes of 2. And if I extended out those lines, you would see that it went up 2 every time it goes across 1. This is how we sort of start the slope field process. Probably see why they don't get you to draw these in like exams usually. And it doesn't matter what y is at this point. When x is 2, the slope would be 4. So any points where x is 2, I'm actually expecting the slope to be 4. So it's going to be quite a bit steeper. It should go up 4 every time it goes across 1. So this slope will be quite a bit steeper there. So m is 4. And we can sort of draw much steeper slopes. When x is 0, the slope is 2x, so the slope would be 0, it would be flat. If x was minus 1, the slope would be minus 2, because it's 2x. So it would be sort of down like that. And then here, the slope would be sort of a lot steeper, like that. So here m is minus 2, and here m is minus 4. Okay. So that's how we'd sort of start a slope field. We can use technology to help us. This is a Desmos app which does slope fields, and you can see that it's pretty much that slope field we were just drawing. Really importantly, y equals x squared we knew was the answer to this differential equation. And you can see that green line sort of goes along the slopes, like it traces along the slopes there. And it depends what your plus c value is, but you might get different answers. So if I go y equals x squared plus 1, you can see that red line there also follows the slopes, it's just a little bit higher up. So depending exactly where you are, you can pick pretty much any point on your slope field you want, and you can draw a solution curve coming off that point just by sort of following the slope lines. Can be a little bit tricky to get that right, but something like that. That would be one possible solution. It's almost like connect the dots, but you're connecting the slopes and matching the slopes at each point. Okay, so we need to do one for dy dx equals y. From the previous video on implicit differentiation, we actually know the solution here is some multiple of e to the x, but we'll see what this looks like. So here, it doesn't matter what x is. When y equals 0, the slope will be 0. So at this height here, I would expect the slope to be 0 all along this axis here. When y is 1, the slope is 1. So at any points where y equals 1, I would expect that slope to be like 45 degrees. Straight across like that. Slope field is very difficult to draw. When y is 2, the slope is 2. So I'd expect it to be a little bit steeper here. And I could just repeat this process and keep drawing it out. It would get steeper again at 3. And then by the time we're up, a lot higher up on this graph, the slope's almost perfectly vertical, because the slope would be like 10 up there when y is 10. So you can sort of see the shapes that come out of these slope fields. You can also go the other way. So y would be minus down here. So the slope would be negative. And then you would get like steeper negative. And then it would get like even steeper. So if I pick any point, like this point here, for example, I could draw a slope field through it. Sorry, a solution curve through it. It would look something like that. Notice that because these slopes here are flat, it's never actually going to cross over that y-axis. I could pick another point here, which is like another solution curve, and we could draw the corresponding solution there. And then we'd sort of want to follow the slopes like that. So those are two possible solutions. This here would be a solution, maybe like y equals 1.8 e to the x or something. I'm sort of using the y-intercept to inform me there. That looks like about 1.8. And then this one looked like y equals minus e to the x. You won't know what the actual equations are because the whole point of slope fields is just to draw a picture to get an idea. Usually you don't know the solution to the differential equation. But anyway, if we look at dy dx is y, we can see the slope field here will update. And if I look at maybe e to the x, you can see that that goes sort of through the slopes. It matches the slopes. Okay, this is what a standard question might look like. Find the gradient of the tangent at 1, 1. So this is similar to what we asked in implicit differentiation. So dy dx, so at 1, 1, dy dx equals, and you just have to sub in 1 for each x and y. So 1 squared, 1 squared, 1 take 1 plus 2. So this would be minus 1 over 2. And you can sort of see at 1, 1, so that would be maybe like here. It does look like the slope is minus a half. So that would be, for example, how you'd fill in the slope field there. Okay, that is good. Now, sketch the solution curve which passes through 1, 1. So I'm going to locate, so there's about 1 there, there's about 1 there. So I'll locate it here, and we're going to sketch the solution curve. So we've got to sort of follow the slopes here, and it looks like it may be getting a bit steeper up there. And then here, we've got to follow these slopes down. And it looks like it may even be bending back on itself a little bit. So something like that. And you could label this something like y, or like the solution 3, 1, 1. And you can imagine that based on whichever one you get, you might get different solution curves. So for example, a solution curve down here might have this sort of shape going on, and then it would sort of weave in and through like that. And the solution curves can look very different depending what your starting point is.